In this lecture, we will talk about reaction turbines. As we know from the previous lecture, Pelton wheel is only suitable for high-head application, and we ask reaction turbines to be used at medium head or low head application. What the name are the names of turbines under this heading? It's Francis turbine, propeller turbine, and Kaplan turbines, all considered as reaction turbine. What is the reaction turbine consist of? Uh, uh, the theory of reaction turbine and the theory how it works. Part of the pressure of the water pressure is converted into kinetic energy through the passage between the group of guide vanes, group of fixed vanes, we call it guide vanes, and then the other part of pressure and the kinetic energy gained in guide vanes spacing can be converted into mechanical energy through the runner blades rotor, and then it will transfer through shaft to the generator. The reaction turbines always consist of main parts. The first one is the spiral casing. The spiral casing is the casing of the turbine which transmits the water from the pipeline or the water tunnel to the turbine runner, which consists of several moving blades. Then the water passes from the spiral casing to the guide vanes. The guide vanes will be distributed around the circumference of the turbine runner. Actually, this guide vanes has two functions. First one is used to direct the water of the runner to the runner blades with a design angle. It means guiding the flow to the runner blades in the design angle, as the designer thought to consider the flow through the runner in some direction. Number two, also this guide vanes can be used to control the flow during load drops. During part load operation, we have to reduce the flow by using this guide vanes without any additional hydraulic losses, because the guide vanes are made in streamlined shape as aerofoil shapes. Here in this sketch we say that the dam and before the dam we can see the water level was high. This high water level can be drawn to the turbine through a pipeline or through a tunnel, we call it penstock, then to the casing, and inside the casing you can see the runner and the guide vanes around the runner, and then after the turbine it goes to the tail race or downstream through a draft tube. Also, after the water gives its energy to the runner, it converts it into mechanical energy. It goes to the generator and through the turbine shaft, and then it generates electricity, and it will be fed to the unified network, electricity network. Okay, as we see this animation shape, it's a casing, and inside the casing there is that rotating part, which we call it the runner. Outside the runner blades, and outside the runner there is another fixed blades, we call it guide vanes, and after that, after the water give its energy to the runner, it goes to downstream from the central opening inside the hydropower plant. Here is the casing. As simply as we see, it will be like made of steel sheets, thick steel sheets to support, it can resist the high pressure of the water inside it, and it will be assembled in the workshop, and then it will be taken after this assembly as a parts. Here the partition between parts is colored with white one, and as we see 1, 2, 3, 4, 5, 6, 7 parts. 7 parts. After this assembly, we can take each part by the crane to put it in the proposed site of it below the ground. It will be assembled above the ground in the workshop, and then it will be transferred to the site. It will be below the ground by about 15 or 20 meters. Then in the center of it, we can put the turbine itself and the guide vanes, etc. As we see at the inlet section, we can see a man or an engineer. This at least 180 centimeter length. You can find as how it is huge of construction. Here, this is a governing system. We have mechanical governor and hydraulic circuit that it can be used during the load drop. Load drop in order to reduce the flow rate to be proportional to the reduced load in order to keep the turbine speed constant. During its opening, as we see here, it's opening, the flow passes through, water flows between, in the spacing between the guide vanes, and goes to the runner inside this circle. Here is guide vanes, are the guide vanes completely closed. This means no flow inside it, through it. This means no power is required, i.e. zero load. We can see here completely open, completely closed, and here completely opened. We have 2 positions. In between, we can take any position, 50% opening or 30, etc., depending on the load itself. Here, as we see, the same thing, that 3 sketch of 3 guide vanes, 3 neighbor guide vanes. The figure A represents fully open guide vanes. This means fully flow or fully flow required at, it can pass full flow, which is required at full load. Section B or sketch B represents the guide vanes completely closed, which corresponding to zero flow rate to the turbine runner, and there is no power generated, which is suitable for zero load application. How they close the guide vanes or move the guide vanes, as we see in figure A or figure B, the same. We have the guide vanes colored in black, about 3 plates. We see three of them in color black, and connected through some links to number 3, which number 3 is a rotating ring, or we call it control ring, with some links. Here is the same. In A, the guide vanes are completely closed. In B, the guide vanes are completely opened. By just rotating this uh, ring, where is the ring? Number 3. Move. Actually, if you have only small turbine, you can operate it by only one hydraulic cylinder. If medium turbine size or just above small size, you can use two hydraulic cylinder to rotate all the control ring. In this shape, in this figure, we can say that it's a huge guide vane. This huge guide vanes, all the huge guide vanes, we cannot operate it by two hydraulic cylinder. As the previous slide, we see here, you can see for huge turbine with huge guide vanes, you can see each guide vane will be moved by uh, by a single hydraulic cylinder fed by high pressure at A and low pressure at B from the same line. They have a common oil line. Line A fed the hydraulic cylinders by the same pressure. It will open or close in the same time. Okay, let us say what is the turbine runner. Turbine runner is a runner of a rotor of the turbine, which consists of several blades, which converts the water energy into mechanical energy. What's water energy? It is the head, pressure head of the water and kinetic energy of the water. It converts most of this hydraulic energy into mechanical energy. What type of runners? Type of runners can be radial or mixed flow. This means the direction of flow inside the runner could be radial or mixed flow. Mixed flow, mixed between radial and axial flow. It's this actually used in Francis turbine, which is applied and suitable for high and medium heads. For another type of axial flow runner, of turbine runner, is the axial flow runner. This axial flow runner used either in propeller or Kaplan turbines, which are used for low head site application. Okay. Let us go to the last part in the reaction turbine. It is the draft tube. What is draft tube? We will see its function after the second slide after this. Let us discuss the following two cases. First case, we have no draft tube. As we see, we have here the water, upstream water of height head above the downstream level. This is the net head or the overall head, and we can transfer the water from the upstream level to the turbine itself, and then the turbine through its water to the downstream level. If we put the turbine on a height Z2 and we keep the turbine to exhaust its water in the atmospheric condition without any or discharge its water to atmospheric condition without any pipe, anything. Let us go and ask about the ET or turbine energy. What's turbine energy? The useful energy that can be transferred into mechanical energy. We simply can say that this useful energy can be calculated as the difference of energy across the turbine. Energy at section 1 minus energy at section 2. Energy at inlet minus energy at exit. If you have energy at inlet, say 100 meters, and the energy at exit 10 meters, this means the exhaust energy will be 10 meters. You only allowable to use 100 minus 10 equal 90, 90 meter. And as energy, you mean you only use 90% of the available energy at section 1. Okay, let us see how can we calculate this. Energy, useful energy E2 equal E1 minus E2, and E1 equal E naught, the energy upstream and the upstream level, upstream water, minus the losses and the tunnel or the pipeline. Okay, E1 equal Z1 plus H1 plus Y1 square over 12G equal H net. Y1 here means the velocity at point 1. If we say energy at 1 equal energy at naught minus the losses in the pipeline. If we neglect the loss in pipeline, E1 could be equal energy in the upstream level, and which will be equal H. Okay, H. And E2, what is energy at exit equal Z at point 2, Z at pressure head at point 2, Z at kinetic energy at point 2. Note that the energy the turbine discharges its water in atmospheric. This means the head at point 2 equals 0. This means that the energy at point 2 equals Z2 plus H2 plus Y2 square over twice G. Then, as H2 equals 0, you can say that E2 equals Z2 plus Y2 over twice G. This means the energy at the exit from turbine will be equal to Z2 potential energy plus kinetic energy at exit, Y2 square over twice. And the useful energy that must be or should be converted into mechanical energy equal E1 minus E2 will be equal to H minus Z2 plus Y2 square over twice G. We will take some numerical example. If we assume H equal 10 meter and Z2 equal 3 meters and Y2 square over twice G equal 2 meters, then H2, if we substitute by these values and this equation of E2, we can find that E total or E turbine equal 5 meter. This means that you only permit to use 5 meter of 10. 5 meter can be converted into mechanical energy from the original assumed head equal 10. This means you only use 50% of the available head as a mechanical energy, as a maximum value, because why maximum value? We know that energy conversion is accompanied by losses inside the turbine. The other example, or as we see here, other case, just connect the turbine outlet at section 2 to the downstream through a conical shaped pipe, conical shape with a divergent pipe. Okay. Then when you connect section 2 to the downstream by this pipe, we cannot assume that the pressure at point 2 equals 0, as the previous case. Okay, let us say that if we, for example, we say that the section area, the diameter at point 3 or section 3 equal double the diameter at section 2. Then the velocity at section 3 equal velocity at section 2 multiplied by d2 over d3 square area. Okay, area ratio. This means if d3 equal twice d2, this means that y3 equal y2 over 4. And also y3 square over twice g will be equal y2 square over twice g divided by 16. And as we assume y2 square over twice g as 2 from the previous example, you can find that y3 square over 2g equal to over 16, which will equal to 0.125. And let us go to estimate the energy at 2 in order to calculate the useful energy E turbine. Energy at 2, now we can say that energy at 2 equal energy at 3 plus losses from 2 to 3 as this equation. E2 equals E3 plus H loss from 2 to 3. And E3 equals Z3 plus H3 plus Y3 square over 2G plus H loss from 2 to 3 means H loss in the draft tube. Okay. And as we know, at point 3 on the water level open area, the potential, and here we have the datum, the potential head of point 3 equals 0 and the pressure head equals 0, atmospheric pressure. We only have y3 square over 2hg and h loss in the draft tube. As we calculated before, y3 square over 2hg, okay, you can find that E turbine equal E1 minus E2, and the E2 now equal Y3 square over 2Ig plus H loss and draft tube. Let us go again to the numerical example as before. H equal 10, Y3 square over 2Ig 0.125, and I assume that the head loss in the draft tube near the value of the kinetic energy at points at section 3 as 0.075. All this give you the turbine useful energy will be 9.8 meter from 10 meter. This means the use of draft tube permits the use of at least 98% of the net head on the turbine. What is the function now of a draft tube? It permits the turbine to use all the available head independent on the turbine level with respect to the downstream level with reducing the exhaust energy at point 3. That is why the draft tube is used. Draft tubes, as we know, permits the use of all the available head, independent on the position of turbine with respect to downstream, and also reduce the energy waste to the downstream. What is the function actually of the draft tube? What happens at section 2? Let us go again and get Bernoulli's equation or energy equation between point 2 and point 3. We can find that E2 equal E3 plus H loss from 2 to 3, and E2 equals Z2 plus H2 plus Y2 square over 2Sg. If we equalize both equations, we can find E2 equal Y3 square over 2Sg plus H loss draft tube. Okay, and if we substitute by the values before, we can find that E2 equal 0.2 meter, very small compared to 10 meters available. Now, from equation 1 and 2, we can find that H2 plus Z2 plus Y2 square over 2Sg equal Y3 square over 2Sg plus H loss and draft tube. We can find in one side H2 equal, and all other quantities goes to the right side. We can find that H2 equal minus Z2 minus Y2 square over 2Sg minus Y3 square over 2Sg minus H loss and draft tube. Now we can find the between square bracket quantities between square brackets Y3 square over Y2 square over 2Sg This represents the exhaust kinetic energy in the first case without draft tube. With a draft tube, we only exhaust y3 square over twice g, and we lose some energy in the draft tube. This means that y2 square over twice g minus y3 square over twice g minus h loss in draft tube, we call it head gain due to use of draft tube with the turbine. As we see, H2 equal minus Z2 minus H gain. This means the draft tube convert the head at the exit of turbine from zero pressure as the first case to a negative pressure. Consequently, this reduces the energy at the hydraulic energy at the exit of the turbine and increases the useful energy, which will be converted into mechanical energy. Let us define the turbine draft tube efficiency or the draft tube efficiency as a ratio between the head gain and the inlet kinetic energy at section 2. Okay, this kinetic energy can represent from 1 to 4% from the available head for low NS runner. Low NS runner means high head application, and this value kinetic energy at exit can be from 4 to 25% for medium head or medium NS runner, and it can represent from 20 to 50% at high NS runner. This means at low head application. This means that we have to save the energy at exit by using draft tube. That energy cannot be used, the energy at exit cannot be used in the runner, but it can be utilized through using the draft tube. This kinetic energy is converted in the draft tube into a pressure energy and with lowering the velocity at the exit. The available or the acceptable value of the velocity at exit can be 1 meter per second. If the exit velocity from the turbine at section 2, say 5 meter per second, and you reduce it at the exit by using the draft tube to 1 meter per second, from 5 to 1 we have a drop in the kinetic energy, and we in the same time we have a gain in the pressure head. Okay, what about the divergence of the draft tube? As we know, it consists of a conical shape with a divergence angle. The permissible divergence angle here not more than 8 degrees in order to prevent separation. As we see here, we have a straight draft tube. It depends on the level or the height of the turbine with respect to downstream. We call it Z. If Z, permissible Z or permissible value of Z is large, this means we can use a straight draft tube. And if we have a margin that can give you, with a small angle, 8 degrees, can give you exit velocity about 1 meter per second without any excessive excavation, we can use a straight draft tube with its efficiency 90%. If Z is small or negative, this is due to cavitation. The permissible value of Z could be negative value or small value with the angle of divergence, permissible angle of divergence, 8 or 9 degrees, cannot give velocity at exit as 1 meter per second. We can only use the bent draft tube. In this case, the bent draft tube has more losses than the straight draft tube due to the existence of the bend itself. But as we see here, the efficiency could be 60%, while for the straight one, it can reach 90%. But the head gain in this case is higher. We are interested in the head gain. Actually, not interested in the